Hi, in this video, we want to take a look at basically an introduction to linear models. All right, so this is the theory-based linear models class. So we're not going to be doing a whole lot with data, but we will be doing a little bit. The focus here is a deeper understanding of linear regression, linear models, linear algebra, and probability and statistics, measure theory, stuff like that. All right, so let's go ahead and just dive on in. So first thing I want to talk about is that linear models are the simplest mathematical structure that we have for modeling a dependent variable that depends on an independent variable. So a dependent variable is our target variable, and our independent variable is the predictor variable. So the equation that we're going to be starting out with is y, the target variable, is equal to beta 0, a constant, plus beta 1, another constant, real numbers, times a real predictor variable, plus the error term. Now, when we say error term, that doesn't necessarily mean like a mistake. Error in this situation, this accounts for everything that can happen that is not accounted for by the remaining part of the equation. So that could be random fluctuations, that could be measurement errors, that could be mistakes in recording, could be other variables that we don't know about, but this is how we are modeling it. Now, in this situation, we're going to go ahead and make the assumption that there's no other variables that we don't know about. And we're saying that x is the only variable that we can measure that has an impact on y. Now, the epsilon term, also, so something about this, anytime you see a Greek letter means that it is a parameter, it's a population feature. And so it's beta, beta, and epsilon. How I write it, you're going to have to get used to how I write my Greek characters. So epsilon accounts for all aspects of the data that is not accounted for in the measurements. So this is not show through very well. I'll do better next time. So x is the measurement error, it accounts for measurement errors, random fluctuations, factors that are outside measurability. Now, something about this modeling system is that we assume that x is perfectly measured. This is a kind of an important aspect if you really want to understand what's going on, that x is treated as perfectly measured. All right, well, what is one of the ramifications of that? Well, when we start looking at the error terms, if I start looking at the scatter plot and I start trying to look at the deviation from the points away from the line, we're going vertically when we start doing those measurements. That we do the deviation between modeled y and y itself, not the difference between the modeled point and the observed point. So if I was dealing with the modeled point and observed point, I would have x and y in there. We don't do that. We only focus on y because we assume that x is perfectly measured. All right, so in this situation, we're saying that the equation is correct. We assume that it's correct. So when we say the word assumption, it's not like when you use the word assume with your dad and when you assume, you make an ass out of you and me. No, no, no. Sorry, Grandpa. We're not going to be dealing with that right now. When we make an assumption, this is something that we have to take to be true, is an axiom. This is something that if it isn't correct, then everything else just falls apart. And that's how we roll when we deal with pure mathematics. Now, something I want to point out is that the line of best fit that we've grown up with at this point is a geometric construct. It comes from projections in linear algebra. Well, if you think about that for a moment, there's no probability and statistics in that at all. That is strictly a geometry construct. That's all there is to it. So we can always use the line of best fit with like very minimal assumptions on our data. I'm talking like finite expected values, finite variances. That's all I really need to be able to use the line of best fit. But if I want to get all the other features that come with linear regression that we've dealt with in our previous data courses, then I need a probability distribution like under the hood to work with. So be able to do hypothesis testing, confidence intervals. Anything that depends on a probability distribution requires additional assumptions. So if I want to be able to trust hypothesis testing and confidence intervals and the other inferences that we get that are dependent on a probability distribution, we have to know what the underlying distribution is, and we have to have additional assumptions. Without those additional assumptions, it's just not going to work out. We can't get that. We can't trust the result. So like the first example of this is going to be like if I try to do a Anova test and I don't have all the assumptions necessary for Anova, then I can't trust the p-value that's spit out, even though the F statistic does give me information that a bigger one implies it's more likely to be significant. But if I don't have underlying assumptions, I can't trust the p-value. So here are some just basic assumptions, and we're going to build upon this, but these are like the main ones that we really want to focus in on right now. So first of all, the equation is correct. It is the correct true equation to be working with, that y is equal to some constant plus a coefficient times our predictor variable plus a random fluctuation term. So remember, the coefficients are fixed and constants, and so we're not doing a Bayesian analysis in this situation. We are frequentist throughout this course. X is perfectly measured, non-random variable, and then we're going to say that epsilon is a normal, 0, and then sigma squared IID, independent, identically distributed. And we're going to say, I messed up on the notation here. This should be sigma squared of y given x. So sigma squared given x is constant. So that is to say that the fluctuation aspect, it does not vary as I change my x values. All right, so that was simple linear regression. So in that situation, I've got one target variable, one predictor variable. Now we want to look at the situation where we have one target variable and multiple predictor variables. Well, it looks very much the same. In this situation, we're going to say that y is equal to the y-intercept plus coefficient times first variable plus coefficient times second variable, so on and so on, coefficient times last variable, plus that epsilon term. So here we're saying that k is a fixed integer, and we're going to say that k is also known. The betas are fixed constants, and they are real numbers. The x's are perfectly measured variables. They're real numbers. And the epsilon is the same as we had for simple linear regression. The normally distributed, mean 0, and we have constant variance with respect to x. Now, when we talk about linear in this class, this is different than linear in calculus. All right, so here, when we say linear, this means that I can put the data on a data frame or a matrix, specifically a matrix. Now, linear algebra and matrix algebra, there is a difference between the two. Almost everything we're going to do is matrix algebra because everything's a lot more concrete. We're going to be working almost exclusively with the real numbers and their subset. If we want to do more exotic things with abstract algebra, start using different fields as entries on matrix, we can do that. That perfectly makes sense mathematically. But for the purpose of being employed, we don't care. So we're going to be really doing matrix algebra almost exclusively in this class. We might get exotic. Maybe if I get bored towards the end of the semester, I might do something crazy. But for now, matrix algebra. If you hear me say linear algebra, you just know we're dealing with matrices. All right, so in calculus, linear means that we have a degree 1 polynomial. Well, in this class, linear means that some way, some shape, some form, I can take the data and represent it on a matrix. Once I have it on a matrix, then I can use matrix algebra to get the line of best fit. That's what we want to do. So for example, let's look at this equation. In college algebra, in calculus, this is not a linear equation because I have sign in here. Okay, but let's change this up for a bit. If I was to look at, if I took a bunch of values of x1, put them into the sign function, and then I took that list of values, then I could take that list of values and make that into a vector. And so then that vector I could put on a matrix. And since I can put that onto a matrix, this is in fact a linear equation for our purpose. Now, in this situation, x1 is not our variable, sine of x1 is our variable. So that's something to kind of keep in mind. Now, why is it that linear models are reasonable? If you think about it, a degree 1 polynomial is pretty simple. I mean, mathematically, could I come up with anything simpler than a degree 1 polynomial for making predictions? If you think about it, no, you can't. I mean, some way, some shape, some form, I need to have the target variable. I need to have the predictor variable in an equation format. What's the simplest version? I mean, maybe a linear equation without the constant. I mean, something simple, but really, you know, y equals mx plus b is as simple as it gets. All right, well, why is that even reasonable to work with? I mean, that seems like a gross oversimplification, right? Well, let's pause for a moment. Let's pause, take a moment, breathe. Breathe, I know it's exciting. Let's say that the true equation that we would like to know, if we had a crystal ball and we could look at it, let's say that the true equation is y is equal to f of x plus some fluctuation term. Y is equal to f of x plus some fluctuation term. And here we say that f is an analytic function with an open interval of convergence around some reference point. All right, so if f is analytic with an open interval of convergence, that means it has a Taylor series. Okay, well, if you think about your Calc 2, Taylor series, I have Taylor polynomials, right? And a Taylor polynomial, I can approximate the entire Taylor series with a degree 1 polynomial. Okay, so what we are trying to do is really, when I have a more exotic function, is when it's analytic, I'm really approximating the degree 1 Taylor polynomial to that analytic function. And so that way, that's kind of like a roundabout way to get what I want. Well, if you think about that, that means that I only have a certain interval of convergence, right? All right, so as long as I keep around that reference point, everything's good. And that reference point is going to be like x bar for us, more than likely. All right, so remember that if I take the Taylor polynomial, degree 1 Taylor polynomial, I have something of this format, and I'm only doing one variable. This generalizes to multiple variables. I can do the constant, first coefficient, x minus reference point to the power of 1. And then I have an error term, and that error term is bounded. All right, well, that error term, what we can do, if I want to make this into something that can be useful to statistics, I can take the original fluctuation, combine it with that fluctuation, and then boom, I have that error term that we talked about previously. So this is a reasonable way to go. We just have to make sure that we're reasonably close to our reference point for the situation that we're in. Now, if we believe that the true function is a linear equation, that's even better. We don't have to worry about all this Taylor polynomial nonsense. All right, so now why do we want linear models? Why is this important? Well, the first one is the sexiest one, prediction. We want to be able to predict y when I know what x is. I want a crystal ball. I know the x value. I want to predict the y value. Another one is to describe features of the data. So I want to describe the relationship of, like, maybe the correlation of something, the strength of the relationship, something like that. Another one is to estimate parameters. This is one that actually comes up a lot in my work, where we're trying to figure out, okay, I only have so much time to spend on this project. and I need to I need to pick my battles. What we can do, we can use linear regression to get the slope. And then the slope will tell me if I put a lot of effort into something, how much will my target variable improve. So what we can use this information to allocate time for how much we're going to put effort into different aspects of the project. We can also use it for variable screening. So one thing I can do, I can go through and do a bunch of like simple, smaller linear regression models, see which variables are useful, and then only use those for another predictive model, such as a neural net or a random forest or so on. Now, another one is to control the output. Now, this is different than prediction. So here, like prediction, I have the X value, and so I want to know what the Y value is going to be. Well, in the control of output situation, I want to change the X value to get the Y value I want. I'm controlling X to have indirect control of Y. Now, the next thing we need to take a look at is analysis of variance, ANOVA. All right, the goal of ANOVA to see is when we do this in regression is to see if our predictor variables as a collection contain informative value towards our target variable. Here, informative value is measured by variance. The more variance I have, the less informative value I have. The less variance I have, the more informative value I have. Okay, so if the predictors account for a substantial portion of the target variable variance, then the predictors have a lot of informative value. All right, well, why is this the way to go? So if we have normal IID, random variable, and we model sample variance with, then we model sample variance with a chi-square distribution, right? I mean, we know about that already. The F distribution arises from the ratio of chi-squared variables. Okay, so variance, sample variance is modeled with chi-squared. If I have, a ratio of chi-squares, I get F distribution. Okay. So we model informative value as a reduction in variance, okay? And so the F test, which arises from the ratio of variances, we can use this to evaluate if we have informative value. And this whole F test situation applied to regression is what we call ANOVA. All right, so let's take a look at an example. All right, so let's say that our model for ANOVA is that y sub ij is equal to mu I and then a fluctuation term ij. All right, so it's subpopulation I and then the jth observation within that subpopulation. And in this situation, we know the number of subpopulations and we know the number of observations within each subpopulation. And here we're saying u sub I is the mean of y for population I. Our null hypothesis is that all subpopulations have equal population mean. They're all equal to each other. Now the alternative is otherwise. All right, take a moment to think about this. Otherwise means anything is different. That there are some ways I can find any two, or something, not any two, I can find two different subpopulations that have different population means. All right, so otherwise, there can be a lot of different situations. Now, basically, ANOVA just works as a flag to say, hey, there's something important inside here. There is you have a gem inside this collection of predictor variables. It doesn't tell you which one is valuable. It doesn't tell you what's useful. You could have, if I have 100 variables, it is possible that 99 of them are junk and one of them is good, or all 100 are gems. We don't know. ANOVA just says at least one thing in there is worth keeping. Now, an alternative model is pretty much the same thing, but now we have a population average And then we have alpha sub I is basically the deviation of the subpopulation from the overall population mean. And then here, our null hypothesis is that all the alphas are equal to 0, which means that they would all have the same subpopulation average, which would mean that they all just have the same average. All right, that's all I've got for now. We'll pick up chapter 2 next time. Take care and goodbye.